Newton's 3 laws of motion. So let's start with Newton's first law, inertia. Essentially, if the net force on an object is 0, like for example, this textbook that's sitting right here. Whoa, okay. This textbook that's sitting right here in my hands, you can see that the force of gravity on it is perfectly balanced out by the force coming from my hands. So that's exactly why it doesn't move. So if the net force is 0, an object will not change trajectory. If I'm in space and I just throw a book deep into the outer space, you'll see that the book will stay at constant velocity. Why? Because there's basically no forces being exerted on it. Whatever star there is out there has almost zero gravitational influence on the book, meaning its velocity is going to keep being constant forever and ever. And obviously not forever. At some point it's going to be sucked into somebody's gravitational influence. But you get what I mean. So, essentially, all this is saying is that the net force is equal. If the net force is equal to 0, then object doesn't change trajectory. If you have a book right here on a table, then you'll figure out that the force being exerted by the table, the normal force, is equal to the force being exerted by gravity, which is why it doesn't collapse in on the table. And thus, since Fg is equal to Fn, well, Fg is equal to negative Fn technically, which means that their sum is 0, which means that this book doesn't move. So Newton's first law is basically just Newton's second law for a special case. So essentially, Newton only has 2 laws at the core. So Newton's second law is that the net force is equal to the change in momentum, or commonly written as ma. So what does this mean? Well, in the case that the net force is equal to 0, then this reduces to saying that the change in momentum is 0, which means that the change in velocity has to be equal to 0. So that's basically just what the first law says. So if we take this book and we drop it, you'll see that it goes down very fast. In fact, it travels faster as it goes farther. So that happens because there's one force and it's unbalanced, which means that the net force is not equal to 0. In fact, the net force is in the downwards direction, which means the momentum will change to be more and more towards that downward direction. And you'll see the same thing happen if I throw it up and then let it go down. Its velocity will stay up, but eventually it will flip. So you can see that common line. Okay. And finally, Newton's third law states that for any action, there will be a reaction. So for example, let's say we have the Earth, and we have a guy on the Earth. Now, of course, the Earth exerts gravity on this guy, but the guy has some intrinsic mass, which means a little bit of gravity is being exerted by the guy on the Earth. And in fact, these two have the same magnitude. So why doesn't the Earth move really fast? Well, that's because F is equal to ma, as stated by the other rule. Earth is way more massive than you, which means that since it has more mass, it will accelerate less. So it will move less when given the same force. So this is the best example of Newton's third law. But if we want something more complicated, let's say we have a man carrying a cart. So this is the cart right over here. And there's a force of friction.
How many pairs? Use three different colors.
Yeah. So there's friction on this road. Free body diagrams for each one. So we can first see that the man has two forces acting on it. So, well, he has the force of himself walking ahead, and then he has the force of the sled kind of pulling him behind. So, meanwhile, the sled or the cart or whatever you want to call it, I'll call it a cart actually. So, this cart right over here has the force of friction acting on it, and it's going this way since the man is dragging it this way, and it has the force of the man pulling it. So you can see this is a pair. So if we look at the ground, then we'll figure out the cart's wheels are also exerting a small amount of friction on it in this direction. And meanwhile, the man walking on it also exerts a force this way.
All right, now we have two more pairs.
Which means we have this pair and this pair. And all of these pairs, each of these pairs have equal magnitude. These two have equal magnitude, these two have equal magnitude, and these two have equal magnitude. So by the first law, since the net force is zero, shouldn't everything come to a halt? Well, no, because these two action reaction pairs, with these three actually, they're all acting on different bodies. One of them, one part of the pair acts on a cart and the other part acts on the man. One part of the pair acts on the cart and the other part acts on the ground. And it keeps going and going. So essentially, it's the same exact thing as the man on the earth example. The action is exerted on one body and the reaction is exerted by the thing that exerted the action. So try punching a wall. That gives the exact same action reaction pair. I mean, your hand punches the wall this way, and the wall punches your hand in the opposite direction. So, one part is exerted on your hand, and one part is exerted on the wall. So, that's how all of Newton's three laws work.